Hello everyone, my name is Anh Pham from UCLA, and today I'm gonna talk about fate and transport of large iron fluxes from benthic sediments along the eastern Pacific coast to the open ocean. And this work is done in collaborations with many people at the University of Southern California and the University of California, Los Angeles, and it is supported by an NSF. So the motivation for this work is when we analyze model results from the ocean model for the full Pacific Ocean with 25-kilometer resolution, we are looking at the dissolved iron concentrations at 200 meters, and we see that iron is being transported from coastal areas where it is released from benthic sediments to the open ocean along the Eastern Pacific Ocean, and the color scale here going from 0 to 2 nanomolar. And when you see the results, our first question is there any observations and measurements that confirm our model results? And it turns out that in the California current system, we do have measurements showing high benthic flux of iron in the Santa Barbara Basin as a function of oxygen and as a function of station water depth. As shown in this figure here, we see that at the bottom water, when oxygen concentrations go to zero, we can have very high benthic flux of iron being released from benthic sediments. And also with our collaborators at the University of Southern California, we can have measurements and observations confirm the release of iron from benthic sediments along the California current in the Hasata Bank and the transport of iron from coastal areas to the open ocean as shown in the figure here, showing sections of iron to total dissolved iron and oxygen concentrations on the Hasata Bank. And we have the y-axis is depth and the x-axis is longitude and color scale showing the concentration of iron 2, total dissolved iron, and oxygen. And we see that whenever we have low oxygen concentration close to the bottom water, we can have high concentration of total dissolved iron and iron 2, and then iron 2 and total dissolved iron can be transported further away from coastal areas to the open ocean. So our goal here is we want to understand mechanisms behind the shelf-to-basin transport of iron along the Eastern Pacific Ocean. But in this study, we're just gonna focus on the northern US West Coast because that's where we have data and observations coming from our collaborators. And to do that, I'm gonna use the regional oceanic modeling system, ROMS, coupled with the biogeochemical elemental cycling model, focusing on the northern US West Coast with 1 kilometer resolution to resolve for the small-scale physical ocean circulation like mesoscale eddies and submesoscale eddies. And on the right-hand side here is a schematic showing the model domain with information about surface forcing, ocean boundaries, and benthic fluxes. We have nitrogen loss to sediments following the approach from Middenberg 1996 and iron input from the benthic sediments following the approach from Sepperman et al. 2010. And on the right-hand side here, we have a schematic showing the biogeochemical elemental cycling model that represents the cycling of oxygen, carbon, nitrogen, phosphorus, and iron, and represents phytoplankton and zooplankton. First, we're gonna focus on the fate of iron being released from coastal benthic sediments, as shown in the figure here, showing the sources and sinks and transport rates of iron integrated over the shelf region defined by the 200-meter isobath and over the open ocean region up to a distance of 400 kilometers from the coast between the surface and 200-meter depth. And we have here the blue arrow showing the transport of iron by ocean circulation, and the red circle here showing the biogeochemical flux of iron And the green arrow here showing external sources of iron coming from either atmospheric dust deposition or from benthic sediments. So we see that in the open ocean, the shelf-to-basin transport of iron is one of the two major iron inputs to the open ocean, second only to the vertical supply of iron. And this iron flux represents about 36% of the total iron input to the surface open ocean, far exceeding dust deposition, and is larger than the net biological uptake of iron in the open ocean, suggesting that the self-to-basin iron transport is a major source of iron to biological activity in the open ocean. And we would like to understand mechanism behind the shelf-to-basin iron transport along the northern US West Coast, and we are doing that by analyzing the cross-shore iron transport as a function of depth and months, along with the cross-shore volume flux also as a function of depth and months, and these two fluxes are average along the 200-meter isobath, and we have here the blue color showing the inshore transport and red color showing the offshore transport. And we can see that there are two major pathways of transporting iron to the open ocean. First in the surface boundary layer and second in the bottom boundary layer, corresponding with the cross-shore volume transport offshore of water in the surface boundary layer and bottom boundary layer. And these two transport pathways are enhanced during the months of June, July, and August, reflecting the role of upwelling in facilitating the transport of iron offshore. And also, we're gonna look at the integration of cross-shore ion transport as a function of months and along with the cross-shore volume flux also as a function of months here. And again, we see the correspondence between the cross-shore ion transport with the cross-shore volume flux. But the cross-shore ion flux is not only a function of the cross-shore volume flux, but also a function of the integration of iron being released from benthic sediments over the continental shelf as a function of months, and ultimately the bottom oxygen concentration as a function of months. Showing here, we see that whenever we have low oxygen concentration, we can have high iron being released from benthic sediments, and we have high transport of shelf iron from coastal areas to the open ocean, and we can conclude that the seasonal cycle of the shelf-to-basin iron transport arises from the interaction between the volume transport flux, benthic iron release, and bottom oxygen concentrations. But if we further analyze the first two figures here on the upper panel, we're gonna see that there are mismatches between the cross-shore ion flux and cross-shore volume flux, especially in the interior layer away from bottom boundary layers and surface boundary layer. When we can have the inshore transport of water, but we can have the offshore transport of iron, and that can be explained if we decomposing the total cross-shore ion transport, the black line here, into different components. The the contribution from the mean ocean circulation and the contribution from the standing eddies. The red line here, the mean ocean circulation is a blue line, and the red line is the contribution from standing eddies, essentially the variation in space of the cross-shore ion transport, and finally the contribution from transient eddies. The green line here essentially contribution from the variation in time of the cross-shore ion transport, and we're gonna analyze the contributions from different components as a function of depth and month. And again, we have the blue color showing the inshore transport, the red color showing the offshore transport. So if we look at the first figure in the right panel here, is a contribution from the mean ocean circulation to the transport of iron. And you can see that the contribution from the mean ocean circulation following the pattern from the cross-shore volume flux with offshore transport of iron in the surface boundary layer and bottom boundary layer, but inshore transport of iron in the interior layer. But if you look at the contribution from standing eddies and transient eddies, we see that iron is being transported offshore in the surface boundary layer and interior layer, but in the bottom boundary layer, iron is being transported inshore by eddies throughout the year. So we can conclude that in the surface boundary layer, eddies work in combination with mean ocean circulation to transport iron offshore, but in the interior layer, eddies work against the mean ocean circulation to transport iron offshore and create a weak net transport iron offshore in the interior layer. And in the bottom boundary layer, eddies actually work against the mean ocean circulation to transport iron inshore. But here, because the impact of the mean circulation is much larger than the impact of eddies, so we still have high offshore iron transport. And finally, if we look at the coast-wide analysis of the contribution from different components of the cross-shore iron transport in the surface boundary layer, interior layer, and bottom boundary layer as a function of latitude with a map showing the location. And again, we have the positive flux showing the cross-shore iron transport, offshore iron transport, and negative showing the inshore iron transport. And the red line here showing the contribution from standing eddy, the green line here showing contribution from transient eddy, and then the blue line here showing contribution from the mean ocean circulation. We see that in the surface boundary layer and bottom boundary layer, we have several hotspots of offshore iron transport here around here, and in the bottom boundary layer in the northern Juan de Fuca region and along the Columbia River and along the Hasata Bank here, and all of this offshore iron transport here are because of the contribution from the standing eddies as shown by the red line here, and it reflects the role played by meanders or separations of the alongshore current and the interaction between the alongshore current with topography. So in conclusions, we see that the shelf to basin transport of iron is a major source of iron to the Northeast Pacific Ocean, and the seasonal cycle of the shelf to basin iron transport arises from the interaction between the volume transport flux, benthic iron release, and bottom ocean concentrations. And also, more importantly, we see that fine-scale circulation like eddies has a substantial influence on the exchange of iron from the shelf to the open ocean. But questions and challenges still remain. We wonder, are there any other observations that confirm the preferential horizontal iron transports in other areas other than the U.S. northern U.S. West Coast, as shown in the figure we see from our Pacific Ocean model, and we wonder, do mechanisms behind these transports differ in other regions? Also, there are many benthic processes are not yet included in our model. For example, in our model right now, we only look at the release of and transport of dissolved iron from benthic sediments and the transport of dissolved iron from coastal areas to the open ocean. But our collaborators at the University of Southern California show in the right-hand side figure here that particulate iron can also be released from benthic sediment and transported away from the coastal area to the open ocean. And that is very important because particulate iron can have interaction with dissolved iron along the transport pathway. And also we haven't yet explored the roles of ligands potentially being released from benthic sediments in protecting iron along the transport pathway. And to address these questions and challenges in future research, it's going to require measurements of various chemical, biological, and physical processes at different spatial and temporal scales. as shown in a study here, that not only the mean ocean circulation at the scales of several hundred kilometers is important in transporting iron to the open ocean, but also we have to consider the role played by fine scales ocean circulation at the scales of several kilometers, like mesoscale eddies and submesoscale eddies. And another challenge is the lack of consistent measurements of iron along coastal areas. So we have here is the data compilation for iron and ligands along the US West Coast from around 1980s until recently. And we only have around 300 measurements for ligands and around 3,000 measurements for iron. We would like to fill the maps of ligand and iron data for the full US West Coast that we see here. And more importantly, the measurements have to be taken consistently to resolve for the variability in season and in space. And with that, I would like to thank you for your listening, and I'm happy to take any questions online with the comments. Thank you so much.